Welcome back to Algorithmic Game Theory. In the last lectures, we introduced the general problems and framework of mechanism design with money, and then we also gained a pretty good understanding of single parameter problems. We could then figure out what it is that makes a mechanism truthful, namely the allocation rule had to be monotone and the payment rule had to follow the formula from Meyerson's lemma. Today, we will go beyond single parameter problems and consider just some arbitrary problems. And for these, we will again show a technique to build a truthful mechanism, although this is not quite as general as it would be for single parameter problems, for which we have an exact characterization of what makes mechanisms truthful. There is no such thing for more general settings. What are these more general settings? Maybe let's quickly recap our definitions. Still, we have a set N of N players or bidders or agents, however you want to call these. We have an outcome space, which is just some arbitrary set. This had a particular structure in the context of single parameter problems. Today, we don't care what this set is. And then each player has a private valuation function, which maps outcomes to real numbers. And then we say that capital VI is the set of possible valuations for player I. Capital V is the set of all valuation profiles. And then we say that a direct mechanism, M, consists of the following things. We have an outcome rule, F, which maps a claimed valuation profile. So each of the bidders claims some valuation function. And this is what the outcome rule takes as the input, and it maps it to an output. And it also has a payment rule, which takes the same input, namely what the bidders claim their values are, and it maps it to a vector of payments, which is just a real number for every bidder. We are still talking about quasi-linear utilities, which means that the utility of a bidder under mechanism M, if his or her valuation is VI, is the value of the outcome that is computed minus the payment that we are imposing on this bidder. And we now call a direct mechanism dominant strategy incentive compatible or simply truthful if for any bidder, any valuation, and any bid, the utility of this bidder when bidding the true value is at least as much as the utility under any other bid, regardless of what the other bidders are bidding. One special case of this was every single parameter setting, but there are also settings which are not single parameter settings. For example, general combinatorial auctions. What would these look like? In a combinatorial auction, what do we have? We have, of course, N as a set of N bidders, and M as a set of M items. And what we can now do is we can assign the items to bidders. And each bidder has a valuation function. Vi, which maps subsets of items to non-negative real numbers. So in our framework, we would therefore set the outcome space X to all partitions of items among the n bidders, where each Si is a subset of M and Si intersect Si prime is empty unless I is equal to I prime. This is not precisely or syntactically, this is not the same problem, because once again here, these functions are something more restrictive, because our more general framework also allows us to say, okay, my value now depends on what items my neighbor is getting. This is fine, but the important thing is to realize this is something that fits into our framework, where we're not so super careful about the syntactical differences, whether we assign a value to such a vector or we assign a value just to any single of these sets. This is actually the same thing that we've also seen in the context of single item auctions. So this is always a little annoying here, that syntactically things do not always quite match up, but it is actually no bigger concern. What could now such a combinatorial auction look like? We might have two bidders and two items. And now we can define the function V arbitrarily. So for example, we might set V1, if bidder 1 gets item A, then they have a value of 5. If they get only item B, then they have a value of 9. And if they get both items, then they also have a value of 9. This is an example of a unit demand function, because the only thing is, do I get an item, or the only thing I care about is what is the most valuable of my items. So in this case, my most valuable item would be item B, and when I'm already getting item B, I don't care whether or not I'm getting item A. We could also now set a similar function for bidder 2, and let's, for example, take this function. It is also a unit demand function. Bidder 2 now has a value of 5 for item A, but no value for item B. And for both items together, he still has a value of 5. So what you see here is that this cannot be described by just a single number. We have one value for item A and one value for item B. And so this is not a single parameter problem. What could this look like visually? It's often helpful to also have the interpretation of this as a maximum weight matching. So in this case, my value for value 1 for item the value of bidder 1 for item A would be 5, for item B would be 9, and for bidder 2 the value would be 5 and 0. Okay. How can we get a truthful mechanism for such a setting? This is exactly the result that we will be showing today. The mechanism that we're getting to know today is the VCG mechanism, which is due to Vickery, Clark, and Groves. And to be precise, we're getting to know the VCG mechanism with Clark pivot rule, because you can also understand the VCG mechanism as a class of mechanisms, out of which we just see one particularly useful, particularly nice instantiation. However, if people refer to the VCG mechanism, they always mean this thing, unless they specify some other particular pivot rule. What does this mechanism look like? We let f, our outcome rule, be a function that maximizes declared welfare. That is, f of b is in argmax of the sum of the bi of x for all b in v. Or, in other words, this function now takes as input the bids, so what the bidders claim their valuation functions are like, and the mechanism, the allocation rule, now treats this just like these were the true values, and under these it maximizes social welfare, and this is what we then call declared welfare. Because now we just take the sum over all bidders, and we now want to maximize what they are bidding, what they're claiming their values are for the respective outcome. And we just take the outcome that maximizes this quantity here. And now what we still do is we still define payments. The VCG mechanism with Clark pivot rule is defined as the pair of this allocation rule and the payment rule, where now the only thing that we actually have to define is the payment of the bidders. And we now define this as follows. We take the maximum over all x, summing over all j other than I, bj of x, and from that we subtract the j which are not in I, bj of f of b. What does this mean? How much will bidder I have to pay? So the allocation that we're performing is clear. This is the one that maximizes declared welfare, although there might be ties. So there we just have to specify some tie-breaking rule if, for example, multiple bidders bid exactly the same thing. But other than that, so we just take the allocation that maximizes this, this declared welfare. And how much do you now have to pay? We have now this interesting difference. What do these two things mean? What's this first thing here? We take the maximum over all x, and then we take the sum over all j other than I, bj of x. This looks a lot like maximizing the declared welfare, except for one thing. Namely, we are not counting bidder I. So this is exactly what we would do when we're maximizing declared welfare, but if bidder I just wasn't there at all. And from that, we're subtracting, again, a sum that does not include bidder I, which again looks like the declared welfare, because we're now summing over all j other than I, bj of f of b. What's that? F of b, that was our allocation that maximized declared welfare. And now, in this allocation, we're taking the sum over everybody other than bidder I. So how much declared welfare comes from everybody except for bidder I? So once again, this was how much declared welfare would we get if bidder I wasn't present at all. This is how much declared welfare are we getting from everybody except for bidder I. So the difference of these is by how much is bidder I actually hurting the others? By how much is bidder I decreasing the declared welfare just because he or she is taking part? This is also called bidder I's externality. Let's maybe first see in a very familiar example, namely a single item auction, what this means. What were the valuation functions for the case of a single item auction? Well, we were again overloading notation. VI was also just the value that the bidder was associating to the item, and not just only the valuation function. And we were then saying VI of x is equal to VI if bidder I receives the item in x and it is 0 otherwise. How would I now maximize declared welfare? How would I do this? I would assign the item to the bidder who bids most. And how much will they have to pay now? Let now I star be the bidder with the highest bid. Well, then what will pi star of B be like? We're maximizing the social welfare but not counting bidder I, and then from that we're subtracting the declared welfare when bidder I is not counted, but it is present in the optimization. How much is which of the two? How would I maximize declared welfare if bidder I would I star, they're called in this case, if they are not present? Well, I would give the item exactly to the bidder with whatever is the highest remaining bid. And then, what is this? What is the declared welfare of everybody, counting everybody except for the bidder who's getting the item? Well, everybody else isn't getting the item, so all of these terms are 0. Which means that the bidder with the highest bid has to pay exactly the maximum bid of any other bidder. I hope this rings a bell, because this was exactly how we did this in a second price auction. What do the other bidders have to pay? If we're now taking some I which is not equal to I star, what do they now have to pay? How do I maximize the declared welfare if everybody except for bidder I is not the bidder with the highest bid? How would I now maximize the declared welfare? Well, I would still give the item to the bidder who's bidding most, because he's not I. So I could still give the item to I star, so this will be I star. And what am I doing if also bidder I is present? I'm giving the item to bidder I star. So, also here, this is B I star. Because I'm not counting bidder I, but that doesn't matter because they're not getting the item anyway. The one who's getting the item is in both cases bidder I star. So the difference between these two things is simply 0. Which means we now recovered exactly the second price auction. But the amazing thing is, also for any other setting, this will now result in a truthful mechanism. And the proof is surprisingly simple. Let's go through this. The VCG mechanism with Clark pivot rule Is dominant strategy incentive compatible? How do we prove this? Well, the first thing that we want to do is we again want to write down the utility of every bidder when they're participating in this mechanism. And then what we'll have to show is that this utility is maximized whenever you bid your true value. So first of all, what will the utility be like? Whatever I'm bidding and whatever the other bidders are bidding, my utility. When bidding BI, the others are bidding B minus I, and my value is VI. This is my value of the outcome minus my payment. So this will be equal to VI of F of BI, B minus I minus the maximum of all x and x. Take the sum of all j which are not equal to I, bj of x, plus the sum of all j and I, j not equal to I, bj of f of bi, b minus I. Where did this plus come from? We had a minus term in our definition of the payments, and because we have a minus here, they together give us this plus. Now what happens on which input? We are now comparing what happens on the input when we bid our true value. So when we set BI equal to VI, and we're comparing this to whatever we're getting when we're bidding some other BI. So on input VI, B minus I, F returns X star, which maximizes VI of X star plus J unequal I Bj of X star. Why that? Because this is now a valuation vector, and we said that we maximize the declared welfare. So F is chosen to maximize exactly this. This looks a tiny bit different now because we're now not writing BI, but rather VI. But that's the only thing that is different now compared to what we were saying before. So if bidder I bids the true value, then this will be the allocation that will be computed. What does this mean? This means that for any other small x, Vi of X star plus the sum of all j, which are not equal to I, Bj of X star, this will be at least Vi of X plus j unequal I bj of x. And in particular, this of course holds for x being some outcome that is computed when bidder I bids something else. So if we now write this out, we'll see here that vi of f of vi comma b minus I plus the sum of all j which are not equal to I, bj of f of vi comma b minus I. This will be at least vi of f of bi comma b minus I plus the sum of all j which are not equal to I, bj of f of bi comma b minus I. Okay, let's now go back. What were our utilities? Our utilities are of this form. It's vi of f of b comma b minus I plus the sum of all bj f of bi comma b minus I plus something. And let's see what we've already derived. We have already derived that this first, this plus this term, this is maximized if we set vi equal to vi. This is what we see down here. Now what we can just do is we can subtract this term from both sides, because it doesn't even depend on bi. This term doesn't depend on bi, so we might also subtract this from both sides. And what we're getting then is that ui of vi comma b minus I comma vi is at least ui of bi comma b minus I comma vi. And this is the exact definition of truthfulness. Cool. So it's, as I was promising, not really difficult to prove this, although you might still think this looks a little magical. And I agree. The first times you see this, you feel what is actually happening here. But the more familiar it gets, the more reasonable it seems. Because what is happening here? Somehow, by setting the payments this way, the incentives are aligned. So each of the bidders has as their goal to maximize the actually their own utility. But now, how do they maximize their own utility? They do this by reporting their true value, because now it is crucial that this allocation function tries to maximize the declared welfare. Because if, for example, all bits are the true values, then it is in every bidder's, we are maximizing social welfare, and so every bidder wants to be a part of this, because the objective function is kind of or in other words, the utility is nothing but the social welfare, except for maybe this term that we're subtracting on both sides, but this is a term that the bidders cannot influence at all. Of course, this would still be truthful if we were subtracting something else here, meaning that if our payments were different, as long as this is a term that doesn't depend on BI. This is indeed one of the exercises to show that the mechanism will still be truthful also when you replace this by another function, although this way, with this Clark pivot rule, the mechanism has some very nice desirable properties, which we see in a bit. But before we get there, let's first go through some examples. Let's now go through some further examples of the VCG mechanism, the first one being sponsored search auctions, and then we'll also come back to combinatorial auctions. In the sponsored search auction, we'll have K, which is smaller than n ad slots, and the more likely, the higher a slot is displayed on the search results page, the more likely it is to be clicked. So we'll have alpha 1 greater than alpha 2 greater than, and so on up to alpha k. These are the click-through rates. And we'll now assign one bidder to each ad slot. And what will my value be? My value will be the value I have, so some real number times the click-through rate of the slot that I'm getting. So this is if agent I gets slot J in X. Let's now keep things simple, and let's just assume that the bidder values are decreasing, and let's now just compute what the outcome of the mechanism will be when they bid now truthfully. How big will social welfare be, or declared welfare, which will be the same. We'll have just the sum of j from 1 through k, vj times alpha j. What is the optimal social welfare without bidder I. Well, what we would now do is we would assign still the first I-1 slots as they were, and then everybody moves up by 1. So bidder I plus 1 now gets slot I, and so on, or more generally, bidder J now gets slot J minus 1. What will now be the payments of a bidder? They will be, okay, first optimize without bidder I being present, which is this thing. But from that, we subtract the welfare that we're still getting when bidder I is present, but we are not counting them. So all we're doing now is we'll take the allocation, but we'll just leave out the ith term. So then, of course, the allocation will still be that bidder J gets slot J. And if you now do this, then you see, okay, the payments are exactly moving each bidder from I plus 1 through k plus 1 up by 1. By how much does the click-through rate increase? So this is the difference in the click-through rates. I'm moving up by 1. This way I'm getting this more in terms of click-through rate, and I multiply this by the respective bidder's value. I hope this sounds familiar, because we got exactly the same formula by using Meyerson's lemma, which is not surprising, because Meyerson's lemma was saying these are the only payments that give us a truthful mechanism, and VCG is actually giving us these exact same payments. So generally, whenever you have a single parameter setting, you can use VCG, or if you do this in any other way, if you just use Meyerson's lemma, you will actually get the exact same thing. For a good reason, because Meyerson's lemma is telling us that it cannot be any different. Unless, of course, you optimize something other than declared welfare, which is possible with Meyerson's lemma. There you're not, this is true even if you're not maximizing declared welfare. VCG, the result is only true where F is an allocation that maximizes declared welfare. Good. Now let's come to a further example, namely a unit demand combinatorial auction. This is an example we've already seen at the beginning of our lecture today. Let's make this a little more precise. Namely, what did I say were these unit demand functions? These unit demand functions are functions such that I'm getting a set of items, but all that matters for me is the most valuable of these items. So I can write down now vi of a set S just as the maximum over all j and s vi comma j. So these are called unit demand functions. How would I now maximize my declared welfare? This is more complicated than before, because I would now have to find an allocation of the items such that everybody gets so that the sum of the values will be maximized. How do I do this here? Well, here, to maximize declared welfare, it is okay to give each bidder at most one item. Because the second item will not count anything. So what will this look like? We are now seeing this as a maximum weight matching problem. Our graph will be N union M, where the weight of the edge between I and N and J and M is Vi comma J. So what will this look like visually? We might now have, for example, 3 bidders, 3 items. How would I find, in this case, the matching that maximizes the sum of the weights? Well, there are effectively 2 matchings, 2 inclusion-wise maximum matchings, namely, I could either take 10 plus 3 plus 1, or I could take 5 plus 2. The one that maximizes the weight, that is, of course, the one with the horizontal edges. So that would be the one that maximizes declared welfare. But how much will I now have to pay? How much will this bidder one now have to pay? What they'll have to pay is 5 plus 2 minus 3 plus 1. Why that? Because we are first counting the declared welfare without him, but in this red allocation. And then what is remaining is 3 plus 1. And then, so this is coming from here. And then we are also just re-optimizing without this bidder being present at all. And then we wouldn't take the red edges, but we would take these diagonal edges. And then we would get 5 plus 2. And the difference of these, this is exactly what bidder I has to pay. The nice thing about the VCG mechanism is that it isn't only truthful, but it also fulfills some other properties, namely being individually rational and also having no positive transfers. These are two properties that we'll now quickly define and also show. The first one is individual rationality. And what is it that it says? If my true value is at least 0 for all x, so if I can never have a negative value, then also my utility, when I'm bidding truthfully, will never be negative. Why that? How can we show this? We actually only have to see what this valuation function, what this utility will look like. Let's write this out. My utility is my value of the outcome plus the value that everybody else declared for this outcome minus the maximum declared welfare if bidder I wasn't present at all. What is this first thing? What is this here? This is just whatever maximizes vi of x plus the sum of all j, which are not equal to I, bj of x. And from that we're subtracting this other term. And here I'm now want to say that this is something you should be really careful because I did this now wrong. bj doesn't take as input f of x, because f doesn't take as input x, but f takes as an input b. So what you should write here is just bj of x, because bj always takes as input the allocation and f always takes as input the declared valuations. Good. So this is where we are. And now what we wanted to actually show was that this is non-negative. And yes, this is of course non-negative, because here we're optimizing over something that is always at least as much as this. So the maximum of this will always be at least the maximum of this. So this will be non-negative, and therefore we see that my utility when I bid the true value is always non-negative. This of course wouldn't be true if, for example, vi of x was always negative. Then we couldn't just avoid that sometimes bidder I also gets a negative utility. But for example, in our combinatorial auctions, my value is always non-negative, and so my utility when bidding the true value will also be never negative. Of course, there are bids that give me a negative value, but those are, for example, in a second price auction, I might, for example, overbid. Then I'm getting a negative utility. But if I bid my true value, I will never get a negative utility. The other property is no positive transfer. Which is that for all bids we have that Pi of b, what was this again? This was the maximum of all j, of the sum of all j other than I, bj of x, minus sum of all j which are not equal to I, bj of f of b. This is non-negative. How so? Well, what do we have here? Here we are maximizing something, and here we are not maximizing the same term, we're just taking anything. But one possible choice for this x would be exactly this f of b, in which case we would have the same thing here. So this has to be definitely higher, or it has to be at least as big as this thing that we have here on the right hand side. And what does this mean? This means that the mechanism will not pay anybody. The mechanism is only collecting money. But in some settings, it might actually be reasonable that the mechanism pays to somebody if you are buying a service from people. So if rather than performing such an auction where you're selling an item, you want to actually purchase an item, and you purchase the item from the one who's offering it the cheapest way possible for you, then suddenly this is strange. Then this VCG mechanism with Clark pivot rule is actually pretty strange, because it still will not pay anybody. But as long as you're in a setting where you're selling things, this is a very good property, because you as the mechanism are not paying anybody, but you're only collecting money. So as we've seen, VCG is a pretty great template for a mechanism. It will be truthful. In equilibrium, you will be maximizing social welfare, and also you have these other nice properties, such that no bidder, when bidding the true value, will end up with a negative utility. However, it is not the perfect mechanism for multiple reasons. There are reasons like a lack of group strategy proofness, which means that if now your friend colludes with you, then this will actually not be a truthful mechanism. But there is even a more severe problem, which is about running time, computational complexity. Namely, what you'll have to do to run this VCG mechanism is you'll have to exactly solve the problem of maximizing declared welfare. And as we've seen, sometimes, for example, in the context of a combinatorial auction, this will be an NP-hard problem, so under our usual assumptions, there will not be a polynomial time, meaning no efficient algorithm. And then VCG won't be truthful if you just use an approximation algorithm and use the VCG payments. And this is what I'd like to have a closer look now, what will go wrong there. Namely, the problem that I'd like to consider is again unit demand combinatorial auctions. And one algorithm that we could consider for this is the following. We consider all pairs of a bidder and an item, and we do this in order of non-increasing claimed value for that item. So each bidder I will claim a value Bij for getting item j, and we now just go through these items, these pairs in non-decreasing order and then non-increasing order, and we'll assign item j to bidder I unless item j has already been assigned. Or bidder I already has an item. So in the language of edge-weighted bipartite matching, this is the standard greedy algorithm, which just considers edges in order of non-increasing weight, and then adds edges greedily to the matching unless one of its two endpoints have already been matched. And it's very easy to see that this will be a 2 approximation, meaning in this case now we'll have that the sum of the bi of f of b will be at least a half times the maximum of all possible bi, the sum of the bi of x. Good. So besides, actually we've made the argument that greedy algorithms are always nice for truthfulness because they tend to be monotone, and also this algorithm fulfills a monotonicity property, namely if you're getting item j and then you increase your bid for item j, then you're still getting item j. But nonetheless, we cannot use this algorithm with VCG payments to construct a truthful mechanism, because recall what we would need for VCG, this factor a half wouldn't be allowed. We would need that we compute the exact optimal solution. And things are even worse here because there's no other way you could define payments such that you will get a truthful mechanism. So let's write this down, what I mean by that. there is no payment rule P such that the pair of this allocation algorithm or allocation rule and P is a truthful mechanism. Or in the language that we used in the context of Meyerson's lemma, F is not implementable. How do you show such a claim? You argue that, well, like we did this in the context of Meyerson's lemma, you argue that maybe your valuation is this, and then you bid that, or vice versa. That this, what you could be bidding instead, because that could also be your true value. And what we'll do now is we'll actually follow a cycle in which then eventually we'll come to the conclusion that there has to be a contradiction to this mechanism that we assume to exist being truthful somewhere. Let's see this in more detail. So assume that there is such a P. And now consider the following kinds of instance. We'll have again 2 bidders and we'll have 2 items. And their values are as follows. Bidder 1, that's something that we will still be talking about, has a value of V1A for item A and a value of V1B for item B, and bidder 2 always has a value of 1 for item A and a value of 0 for item B. Bidder 2 will always bid truthfully. And bidder 1 can have the following valuations. Namely, we might have that the value that bidder 1 has for item A is 1 minus epsilon, and the value for item B might be epsilon. Or there's another possible valuation that we're considering, namely that the value for item A is 1 plus epsilon, and the value for item B is 1 plus 2 epsilon. And the third case is that the value for item B is for item A is 1 plus 2 epsilon, and the value for item B will be 1 plus epsilon. Where epsilon should be small enough, more precisely, we want it to be less than a third. Good. What will we do now? We will see, okay, your value might be V1, and then you should not benefit from reporting V2, for example. Or if your value is V2, you shouldn't benefit from reporting V1. And this way we get to a couple of inequalities. And eventually this will now turn out that these mechanisms which would make the mechanism truthful cannot exist because we get to a contradiction. So what would have to hold? We would now have to have the following. By truthfulness, we would need that bidding V2, so and by that I mean bidder 1 bidding this second valuation here. If this is the true valuation, this should give a utility of at least the utility it gives when they bid the first valuation. And of course the value will still be, this is always the true value, and we're always seeing the second line here. What happens if you bid this much? Well, let's go back here. What will happen? Which of the two items are you getting? We start by assigning the item for which the value is highest. So this in this case would be this 1 plus 2 epsilon. This means that bidder 1 will get item B. And what happens if they bid this first valuation instead? Then first bidder 2 will get item 1, and only then, so item A, and then only then item B is left, so they also get item 2. So in both cases, bidder 1 will be getting item item B, and this means now they get the value for item B minus whatever they have to pay. And you see the payments, of course, don't know the true value. They only know the bid. And by this inequality, we now see, okay, when bidder 1 is bidding the second valuation, the payment is at most what they have to pay when they're bidding the first valuation. You could also swap V1 and V2 here, and you would also then see that this also holds the other way around, but we don't need this for our argument. Now we can do a similar thing for the case that the true value is the third valuation. Then you wouldn't want to bid the second valuation, or more precisely, you shouldn't benefit from that. Once again, what items are you getting when? When you bid this much, then as we saw, you're getting item B, and when you're bidding this much, then you're getting item A. Okay, so we'll now have here, there we're getting item A, we have a value of 1 plus 2 epsilon for that item, and we pay something. And here we'll get item B, for which we have only a value of 1 plus epsilon, and we'll also pay something. This gives us also an inequality, namely that when you're bidding the third valuation, then you're paying at most epsilon more than when you're bidding the second valuation. And now we'll do actually this same argument once more, but now for the case that your true valuation is the first valuation. And also when your true valuation is the first valuation, then you shouldn't benefit from bidding the third valuation instead. When you're bidding the first valuation, then, as we've seen before, you're getting item A. What's your value for item A? You're getting item B. Your value for item B is epsilon. When you're bidding the third valuation, then you're getting item A. So we'll have here that this is epsilon minus what you have to pay when you're bidding the first valuation. And what we'll have here is the value you have for item B minus what you have to pay when you're bidding the third valuation. And this tells us that P1, when you're bidding the first valuation, is at most whatever you're paying when you're bidding the third valuation and now minus 1 minus 2 epsilon. And now just see all of these together. You see this inequality, you see this inequality, and you see this inequality. And you can now start wherever you like. For example, start here. Then you have an upper bound of this. Then you can use this upper bound. You can use this upper bound. And eventually you will reach, at some point, you will have to reach a contradiction. So all of this together will be a contradiction, so this payment rule cannot exist. So once again, how did this argument work? And how do you generally show that you cannot make you won't be getting a truthful mechanism? You can always compare these things that maybe your true value is this much and you're telling the truth, or your true value could also be something else. And always you compare what could be your true value, what happens if you bid that true value, and what happens if you bid some other value, but this could also be your true value. And now all these inequalities that you're getting, you all combine together. This is the way we did this for Meyerson's lemma. There things are pretty straightforward. You can also derive a characterization of truthfulness via this kinds of inequalities. Namely, if you say, okay, all of these inequalities have to be fulfilled, this also gives you some kind of a characterization on what algorithms or what outcome rules can actually be implemented truthfully. But the point I wanted to make here is that VCG payments won't make it truthful, and also there is a general problem when you use approximation algorithms. At least when you go beyond single parameter settings. In case of single parameter settings, all you have to care about is your algorithm monotone. Here now, this will be far more complicated, and very natural algorithms fail to fulfill the necessary properties. And this is also the reason why combinatorial auctions in polynomial time designing truthful mechanisms, this is still an open problem. There has been quite an enormous progress. There are many great mechanisms that do run in polynomial time and that are truthful and still get a reasonable approximation guarantee. However, it is still in many ways an open problem. For example, can you do this via a deterministic mechanism? Solving only the allocation problem in polynomial time approximately, that's something easy. But then as soon as you want this truthfulness, then things will actually go wrong. Good. So this concludes our discussion of the VCG mechanism. I hope you understood most of this. Otherwise, please do ask any questions. And see you next time. Stay safe. Bye.